Okay, this is the third presentation in the Work Energy Power series. Make sure that you've watched the energy presentation, the work presentation, and now we're going to talk about combining work and energy. And we'll do that by talking about the work energy theorem. All right. So energy, we know, is the capacity to work, the capacity to do work. And energy comes in all different types of forms: electrical, mechanical, nuclear, water, what have you. And any of those forms of energy, all those forms of energy have the capacity to do work. Work is the application of a force over displacement, taking a very mechanical approach, as opposed to aerobic work, which is a little bit different. And we can talk about that later on in other presentations. So from a mechanical perspective, work is force times D, or we would say more generally force times d times cosine theta, where the theta is the angle between the force and the displacement vectors. So really FD is just that both vectors are parallel to each other. Interestingly, work and energy are scalars. Power is also scalar. All right? They're not vectors. These are scalars. They do not have direction associated with them, although we often use whether or not something's positive or negative as telling us something else about what's going on. Work and energy have the same set of units, joules. Okay, now remember the base units of work using the equation FD is Newton meters, but we do not use Newton meters to describe the units for work because we reserve Newton meters for torque. Energy, all different forms of energy, all right, at the end of the day, they all have units of joules. Now, some of you may be in the nutrition world and you may know energy in a set of units is calories. Well, calories and joules can be converted from one form to another. They're just different. They are representing, in essence, the same thing, but just the math behind it is a little different. All right, so energy, work energy theorem. Let's dive into this a little bit. Oh, I got to share my screen. All right, sorry, I meant to have this slide up while I said all that. But energy, the capacity to do work. Work is the application of force over distance, and both work and energy have the same set of units. All right, mechanical energy. All right, now I'm going to focus in on mechanical energy here, as opposed to other forms of energy, because this is biomechanics. If I'm in physiology, I'm going to talk probably more about physiological energy. If we're going to in nutrition, it'd be a little bit different. But here we're going to talk about mechanical energy. So energy related to the motion of an object, and there's two basic categories of mechanical energy: potential energy and kinetic energy. Remember, there's all different forms of energy. Potential energy is the capacity to do work based upon position. Now, often we think of potential energy as an equation, I'll have that in just a second, as mgh, mass times gravity, acceleration due to the force of gravity, times the height of the object. What that means is if I'm holding a bowling ball up, I have the capacity to do work on the floor if I drop the bowling ball. I have the capacity to apply a force to the floor and then move the floor some displacement, do some damage. All right. So potential energy, it has the potential to do work, the potential to apply a force over some distance, and we can calculate the potential energy based upon position. Just to keep jumping around to different areas, remember we have potential chemical energy as well, and that's the food that you're eating. When you look at the calories, that is describing chemical potential energy. All right, we also have potential energy in the mechanical world based upon elastic behavior. So if I take a rubber band, that rubber band has the potential to do work if I have it stretched. That is, if I release that rubber band, it's going to want to return back to its original position. So by stretching the rubber band, I've given the rubber band some potential energy, some potential to apply a force over some distance. I also could have a compressive spring where I can compress that spring and it wants to push back outwards as well. That's potential when I have compression or if I stretched the spring. And we're going to talk about that, especially when we start talking about shoes, or there is a whole nother way to study the mechanics of movement running by looking at the energy of the person, both in potential and in kinetic. And we'll use a mass spring model often to explain how a runner moves based upon changes in elastic behavior of the body, or description of that elastic behavior. Okay, the other type of other category of energy that I want to cover is kinetic energy. This is, again, the capacity to do work, but based upon movement, okay? Based upon movement. So kinetic energy is the capacity to do work based upon movement. Potential energy, the capacity to do work based upon position. Energy is the capacity to apply a force to move an object. Remember, to have work done, we need to apply a force and that object needs to move. So two things, the object needs to move. All right, potential energy, a little bit more on this. The energy due to position of an object, I mentioned the equation already, PE, potential energy, is mass times the acceleration due to the force of gravity times the height of the object. The units, joules. All forms of energy have units of joules. So any form of energy I put down on paper here, any form of energy that I've mentioned will have the units of joules. The other form of energy that I mentioned in terms of potential energy is the energy stored in a spring, 1/2 kx squared, where k represents how stiff a spring is. So the stiffer a spring, the harder it is to compress it, or the harder it is to stretch it out, okay? X being how much compression or how much stretching that spring undergoes, okay? So this is just a little cartoon of that. This is the unstretched spring. I stretch it, that X is that X in here, and it is squared, so 1/2 kx squared. And that's the potential, that's the capacity to do work based upon stretching that spring. So once I release that spring, it's going to want to apply a force, and it has the potential to move an object based upon how much energy there is upon stretching it. Again, units of joules. This is just the cartoon of potential energy, mass times the acceleration due to the force of gravity times how high that object is. And that has the capacity to do work on the floor in this example, based upon how high it is. And this graph is just a representation of how stiff a spring is. On this axis is how much force I'm applying to the spring, and then how much displacement the spring undergoes. So these are three different springs, and the slope of the force over force displacement plot represents how stiff the spring is. So if I apply a lot of force, so if I apply a lot of force and I only get a little bit of displacement, that means that's a stiff spring. I can have the same displacement and apply a very little amount of force, and that's a very compliant spring, so it's less stiff. So the slope of this line represents how stiff a spring is, and that is just an interplay of how much displacement we get for a given force. So it's almost the reverse. In order to stretch a spring, I need to apply a force. I need to do some work on the spring in order to give it potential energy. That's that interplay of work and energy. All right, a little bit more on kinetic energy. It's the capacity to do work due to movement. And we do have translational and we do have rotational kinetic energy. And we'll talk about these throughout the semester, because we will be dealing with a bicycle where we have wheels rotating. And we'll also be talking about running and swimming where we have translation. So translational kinetic energy is 1/2 mass of the object times how fast that object is moving squared. Simple equation. Units are joules. Rotational energy, we just use the rotational world component, so 1/2 moment of inertia times angular velocity squared. Same set of units, joules. And remember, units for mass are kilograms, units of velocity are meters per second, units for moment of inertia are kilogram meters squared, units of angular velocity has to be radians per second, not degrees per second. All this is saying is that a truck with this mass, with whatever velocity, has the capacity to do work. This is such a morbid example, capacity to do work on an object. I pulled this from a textbook, believe it or not. All right. So the capacity to do work based upon movement, and that kinetic energy is a function of two things: how much mass the object has that's being moved, and how fast that object is moving, either in the linear world or in the rotational world. Okay, so now the work energy theorem. Work and energy have the same set of units, joules. They're related to each other. The amount of work done on an object by a net force is equal to the change in kinetic energy. This is the work energy theorem. The amount of work done on an object by a net force, or this is just all the forces added together, is equal to the change in kinetic energy. So if we take the kinetic energy at one moment in time, initial, and then take the kinetic energy at another moment in time later on, the final, if there's a difference between these two amounts of kinetic energy, we will have done work. We will have applied a force over some distance. We would have transferred energy from one object to another. This is not describing transformation of energy. This is kinetic energy only. So it's kinetic energy at one moment in time, kinetic energy at another moment in time. We use this concept a lot in biomechanics because we start talking about terms like energy absorption or energy generation. All right. Remember, we cannot actually create nor destroy energy, but we can transform it from one form to another. So if the energy at this moment in time is not the same, if the kinetic energy at this moment in time is not the same as the kinetic energy at this moment in time, we will have had work being done. That means that this energy, if we add up all the energy at this moment, is being transformed to some other type of energy other than kinetic energy. Maybe heat, maybe sound, okay, whatever it is. But it may be potential energy even, but it's not kinetic energy. So the work energy theorem is specific to kinetic energy, energy due to movement. So we do this a lot in our biomechanics world, and we talk about we talk about shoes and how much energy a shoe will absorb upon impact. Well, all we mean is the kinetic energy that's present at the time of impact ultimately is going to go to zero where the person is moving downward and stop being moving downward. And that shoe is absorbing that impact energy. It's transforming the energy from movement, 1/2 mv squared, to something else. And that other type of energy may be spring potential energy. And you all know, I'm sure you've heard about the shoes like the Nike 4%, or shoes that are putting carbon insoles in them. The whole idea of those shoes, or an idea of those shoes, is to store some of the energy. See, now we're getting more complicated, believe it or not. We're transforming the energy at impact into spring potential energy. And then we want to, after impact, allow that spring potential energy to do work on the person to move the person forward. So it's an interplay of transforming energy from one form to another and then back to the other form. So going from kinetic energy to spring potential energy back to kinetic energy. All right. All right. So yeah, this gets a little bit circular at times. So work energy theorem. It's the net work done on an object is equal to the change in kinetic energy. Very specific to kinetic energy. Okay. The equation, we need to know the kinetic energy at the final moment in time, and we need to know the kinetic energy at the initial moment in time. The difference between those two moments in time in kinetic energy is work. Okay, now I'll go through a couple descriptors here. If the final kinetic energy is greater than the initial kinetic energy, that means the object's speed has increased. Remember, 1/2 mv squared. So if 1/2 mv squared is greater final versus initial, mass of the object isn't going to change. At least we're not going to consider mass of the object is not changing. So therefore, v has to change, and that means if kinetic energy final is greater, that means that the final velocity is greater than the initial velocity. That means the object sped up. That means the work done on the body is positive. Word on the street, we would say energy is generated by the system, or we've done work on the object and we've caused that object to speed up. I push on the object, it's initially 0. I start speeding that object up. The kinetic energy at the beginning of that example is 0. The final kinetic energy is based on 1/2 mv squared. It's based on how fast I get the object moving. I've transferred energy from me to the object. The amount of energy I've transferred is the work done. And I've generated energy. I've moved the object. Okay, now let's go the opposite. If the final kinetic energy is less than the initial kinetic energy, that means the object speed is decreasing. The work done on the object is negative. Remember, work and energy are actually scalars, okay? They are scalars. So they do not have a direction associated with, but here's where I start using the positive and negative sign to do some interpretation of what's happening to the example. So work done on the object is negative. Word on the street, we would say energy is absorbed by the system. Okay, energy. So now once I get that object moving, that would be the initial kinetic energy for this next bullet. And it has some kinetic energy based on 1/2 mv squared. Let's say I want to stop that object from moving. I start applying a force in the opposite direction that the object's moving, and I slow the object down. And my final kinetic energy is now 0. The work done on that object is a difference between the kinetic energy initially and the kinetic energy final, which is 0. So I have some kinetic energy to begin with. I stop that object, and I cause kinetic energy to go to 0 in that example. The work done is a difference between the kinetic energy final minus initial, and I would say I'm absorbing the energy of that object, or if I'm catching the ball, I'm absorbing the energy of the ball moving. Okay. That would be word on the street. Again, we don't create or destroy energy. What we do is we transform it from one form to another. So all I'm doing, if kinetic energy final and initial are not the same amount, I'm transforming energy to some other type of energy. I don't know right now, okay? Right now, this is a very simple math equation. It's not telling us what other forms of energy are being created. It could be heat, sound, whatever it is. Potential energy, spring, potential energy, position. It could be any of those. That's not what this is telling us. All it's telling us is the kinetic energy is different. That means work was done. And our interpretation of that is as either we're generating work or generating energy or absorbing energy. Those are not actually correct phrases, but we use them all the time. The total energy, mechanical, heat, whatever, is always the same. Energy is conserved. The work-energy theorem is specific to the change in kinetic energy. Okay, all right, so summary, you got to know mechanical energy, and that's what we're focused on right now. Potential energy, the capacity to do work based upon position, and that position could be, based upon a linear, raising the object upward, or could be based upon compression of a spring. Kinetic energy, 1/2 mv squared. Capacity to do work based upon movement. The work energy theorem is specific to looking at changes in kinetic energy. The amount of work done on an object by a force is equal to the change in kinetic energy. The amount of energy transferred from one object to another is determined by the change in kinetic energy. If kinetic energy is not the same at two moments in time, that means energy has been transformed to some other form of energy other than kinetic. And finally, energy and work have the same set of units. Okay, that's the work energy theorem. Thanks.